with Valeriya Korol. So she did her master's in Bologna, after which she obtained her PhD in Leiden. And among other things, she obtained a Kavli Fellowship. She obtained the Rubicon Fellowship, which is one of the actually most prestigious fellowships in the Netherlands for postdocs. And also on top of that, Gruber Fellowships. And she's now actually a postdoc in University of Birmingham and University of Cambridge in the UK. And she just today actually has an archive paper on studying the Milky Way structure and dwarf galaxies with Lisa, which she will talk about today. And just as a reminder, she still has a few spots left for today if you want to teach her, so feel free to reach out.
Okay, so can you hear me? Yeah. So in this talk, I would like to show you that one day we will be able to study our galaxy using gravitational waves in the same way as we studying it now with the electromagnetic waves. So despite the fact that we are now able to resolve billions of stars around us and see a detailed structure of the Milky Way surrounding us, one of the major difficulties still remains to understand the global properties of our galaxy, so its shape and its geometry. And the way we address this problem is by dividing our galaxy in discrete components, like the bulge, disk, stellar halo, and then by defining their structural parameters like masses and scale radii, so we can compare those with the other observed galaxies, and we compare our galaxy as well with numerical simulations to test our galaxy formation theories and the lambda CDM paradigm. However, even those structure parameters are not easy to measure. Let me show you a couple of examples relevant for this talk. So on the left, you see the disk scale parameter, so the disk scale radius on the x-axis and the disk scale height on the y-axis, and the color markers are different measurements using different stellar tracers. And as you can see, there is a wide range that they spread into, and that there is no clear consensus yet on their values. And on the right, you see the bar scale parameters. So on the x-axis, the bar axis ratio, and the viewing angle, so the angle under which we see the bar from the position of the sun. And again, you see that there is a wide spread in both directions. And the main difficulties that we are facing here is a number of biases for different stellar tracers, the fact that you have dust extinction at optical wavelength, and because distance is always difficult to recover. So I propose to overcome these difficulties by using gravitational waves. And this will be possible with the future LISA mission. It is an ESA-led mission that will consist of 3 spacecrafts linked by lasers. And the arms of this interferometer will be of 2.5 million kilometers. So this will be literally a giant gravitational wave observatory in space. It will follow the Earth's orbit trailing behind the sun, and the date for the launch at present is in early 2030s, and the mission will last over from 4 to 10 years. And the major core science goals for LISA are observing merger of massive black holes that are hiding in the center of galaxies, and this will be possible with gravitational waves all across the universe, so from our galaxy down to almost Big Bang, but also observing stellar origin black holes that are falling into massive black holes, and we can use these sources to map the space-time around supermassive black holes using the stellar mass 1 as a point particle. And the other major goal for LISA is observing a big number of stellar binaries in our own galaxy. And the most numerous of those are binaries composed of two white dwarfs. I will call them double white dwarfs and indicate with DWD. And I believe that they can be used as galactic tracers because they will be very numerous in gravitational waves. Several tens, from few to several tens of thousands will be detectable with LISA. They are also luminous in gravitational waves so that you can see them all the way through the galaxy. In principle, this sample will have no contaminants because we will see only gravitational wave sources, and we will be able to determine their distances directly from gravitational wave signals. And to make predictions for galactic studies, I first need to construct a mock galaxy. So for that, I use binary population models from Sylvia Tonen, and she's using binary population synthesis code SIBA. And this is one of her populations. So these are the properties of the binaries as they become double white dwarfs. So we initialize them as at the zero age main sequence, evolve them until both turn into white dwarfs, and these are their orbital periods and chirp masses. So this is the quantity that we will observe in gravitational waves. Yes, so they tend to occupy this lower right angle of the parameter space. Their typical chirp masses at around 0.5 solar masses, and their orbital periods accumulate down to a very low one, up to hundreds of days. So I cut this population to the LISA sensitivity band. The color here represents the formation time of the binaries, and you can immediately see the trend. So the most massive one take less time to form, and the less massive one can form up to a Hubble time scales. Then in this dashed dot lines, I also plot in their merger times, if I consider that they in spiral only due to gravitational wave radiation. So the sum of this time scale plus those gives you an indication on the lifespan of the binary. And with this line, I roughly show where white dwarfs with the different core compositions are in these populations. So, for example, if you model a young stellar population, you would mainly have this kind of binaries with the with the carbon-oxygen core composition. And if you model old stellar population, you would end up to have this low-mass helium white dwarfs. The next step in my research is to give them a place in the galaxy and a birthday. And for that, I assume a Milky Way potential. So this is the potential and the respective density distribution. And for this first part of the talk, I'm just using a smooth analytical potential with the spherical central bulge, an exponential disk, and a spherical halo. And I use a star formation history from a numerical simulation that peaks at early time and then decreases down to roughly 2 solar mass per year at the present time. And the combination of these three components of binary population, Milky Way, and the star formation gives me my mock galaxy. And the next step is then to understand which of these binaries will be observed by LISA. And for that, I'm using a LISA pipeline that was designed to process a large number of quasi-monochromatic sources. And this pipeline basically takes my catalog and iteratively removes the bright one until it converges. And what you're left with is the catalog of observed sources and a background of those that are unresolved, that remain unresolved by LISA. And what I find is that out of millions of double white dwarf binaries that are in my mock galaxy in the LISA band, 26,000 will be seen with the signal-to-noise greater than 7. That is the nominal LISA signal-to-noise threshold. This is after 4 years of mission. 5% of them will have high signal-to-noise greater than 100. And this means that from these binaries, we will basically know and measure everything. And this is the cumulative distribution of the relative error on the distance in blue, and on the sky localization from LISA in red dashed line. And for the following studies, I select those that have relative errors on the distance lower than 30%. And typical sky position error for LISA is, for these binaries, is around 10 degrees square. And this is the map of the LISA signal to noise in my mock galaxy. So this is the galactic center, and this is LISA. And basically the color is the signal to noise itself. So you see, what I wanted to point out is that you see magenta and yellow colors everywhere in our galaxy, in this mock galaxy. And this is unusual. It's different from what we used to in electromagnetic observations, because we would normally have better measurement around us, and then they would get worse and worse as you go further. But in gravitational waves, you have good measurements everywhere. And the secret to this are the high frequency binaries. So if your binary is above, emits gravitational waves above 3 millihertz, that corresponds to roughly 10 minutes orbital period, that binary can be detected everywhere. And this is because higher frequency has intrinsically, they are louder. LISA is the LISA sensitivity curve bucket is centered on exact 3.5 millihertz. So LISA is the most sensitive in those frequencies, and we don't have any backgrounds in that region of the LISA band. And I found a cute way of visualizing this by working at the music project. So here I basically took all the binaries in my galaxy, and I translated their frequencies into the piano frequencies. I divided them in octaves and then in notes. So here I'm showing you the second octave, and as you can see, we're mainly exploring space around us. If we go to a higher octave, we start exploring larger space, and you see the trend in color. So the lower frequencies are still around us, and when we go farther away, we start seeing binaries with the at the higher nodes. And when you get to the center, you basically see them all, and this is where we are at the millihertz regime. As you go at the higher octaves, you still see binaries everywhere, but they become rarer. And this is because they just merge faster, so they are gone by now. So what I did next is to take their density distributions, and I divided them in bulge and disk. And what I'm doing here is just binning binaries in spherical shells in this plot, in cylinders here, and then layers here. And I divide my counts in by the volume of the shell, so that I can get the number density. And this is shown by magenta points. The blue line, the black line here is the underlying model, so the one that I used in the first place to generate the galaxy. And the blue line with the blue band is the fit to my data using the input model with the 3 sigma boundaries. So what I found by doing this exercise is that I can recover the bulge scale radius to 2%, the disk scale radius to 3%, and the disk scale height to 15%. And this is competitive measurement with those using optical stellar tracers. So the next question that I asked myself is, okay, we can see the whole galaxy, we can describe its shape, but can we see also like the details in its structure? And for this, I slightly changed the recipe. So instead of taking a smooth analytical potential, I'm using a numerical simulation from Elina Dongia, in which she used hybrid hydro and antibody simulation that naturally develops the central bar and the spirals. And I repeat the same procedure. I populate this simulation with binaries, and this is the result. So this is a straight way to interpret. This is where I start from, and this is what I see with LISA. So all the colored pixels are a number density of LISA detections, and the whites are those pixels where we don't have detections. And you can immediately see the central bar. And maybe perhaps you can also see the hint of the spirals in here. And this was actually a master project of a student that I was supervising last year in Leiden, Martijn Wilhelm, and he's basically ready to submit this work very soon. So what we did with this density distribution is to analyze it, we transform it in Fourier space by just applying Fourier transform on this on the density. And here I'm showing the M2 Fourier mode normalized to M0, where M0 is just the total mass of the galaxy. So you see this first peak that rises from the bar, and the bar length is of around 4.5 kiloparsec. And the second peak rises from the spiral arms. And what we did here, we focused only on the bar. We assume a density distribution. We just picked the Gaussian density in the 3D Gaussian. And we apply the Fourier transform, and we fit this mock data with our Gaussian density. And what we found that we can recover the bar length to 10%, bar width to 4%, and even the viewing angle, so the angle under which we see the bar. Okay, so this previous work, in which basically we understood that we can see binaries everywhere in the galaxy and even at the opposite edge, so opposite edge to us. Then we asked ourselves whether we can see the same double white dwarfs even beyond the Milky Way. And here I'm exploring a double white dwarf parameter space, so orbital periods versus chirp mass. The color here is their merger time. So for example, these white squares are known double white dwarf binaries, and for example, this white square is the Warrens-Brown 12-minute binary system. And the color lines here are the LISA detection thresholds at the distance of large Magellanic Clouds, small Magellanic Clouds, and this is at the distance of Andromeda Galaxy. So what we found here is that if your binary has period less than 10 minutes, you can see it up to Magellanic Clouds, no matter what its chirp mass. And if you want to go further, you would bias yourself to shorter orbital periods and higher chirp masses. And this corner of the parameter space actually represents candidate double degenerate supernova type 1a progenitors. So LISA turned out to be also very good instrument to explore the progenitor of the type 1a supernova, not only in our galaxy, but also in the local group. And the last few questions that I want to answer are if we can see these binaries in our local group, how many we expect them in the dwarf satellites around us. So in this paper that appeared today on arXiv, we model double white dwarf population in the dwarf satellites by fixing. Here we fix the star formation history. This is one example. I consider a few of those. We fix IMF and the metallicity. And we change here the mass of the satellite and its distance. And the color here is the number of LISA detections. So this line shows you where we have one detection. So what we found is that in satellites with masses less than 10 to the 6 solar masses, it is unlikely to have LISA detections because they are just not massive enough to produce such rare binaries. But if we go to higher masses, so for example, between 10 to the 6, 10 to the 7, we can we start having detections up to, and we can see those up to a few tenths of kiloparsecs. So for example, Sagittarius dwarf galaxy will be visible by LISA. And even at higher masses, so like Magellanic Clouds, you can see them basically everywhere in the within the Milky Way virial radius. And here I'm reporting the number of detections, and this is actually for this for exponentially declining star formation rate. It's history. It's not the most optimistic star formation history, especially for those dwarf galaxies that are still star forming. So we actually went and we tried to fine-tune star formation history for this group of dwarfs. And actually what we found that these numbers are, in some cases, are higher. So for example, in Magellanic Clouds, we get something like 200 LISA sources, so they will stand out in the LISA data very clearly. And here I'm showing you a different work from the Birmingham group, where we explore whether we can actually distinguish these overdensities and say that those are our satellite galaxies. So in red, you see the density of the foreground double white dwarf. So this is the Milky Way disk, and the bulge, and the yellowish colors represents the halo. Then what we did is to inject some test binaries in all satellites. So the stars represent those satellites where we can see binaries, and the points are those that are not detectable. So out of 50 satellites, you see that many of them are actually stars. And the ones that have a circle around them are those where we also expect at least a few LISA detections. So what we found is that, well, Magellanic Clouds will be clearly visible because they do not overlap with the foreground sources. Sagittarius will, with some data analysis, will be also visible, and at this position, we would have something like 5 foreground sources. Meanwhile, we expect 10 with the fine-tuned star formation history. Sculptor maybe, and Fornax unfortunately is too far away to have detections. And the blue color here basically was showing you the sky uncertainty in the LISA data. So we will actually have quite good sky localization for all of them, so we will be able to narrow down at distance 3D position of these binaries and unveil some of the Milky Way satellites in the LISA data. So to conclude, I just want to give a brief summary. So I showed you that LISA is an all-sky survey. It doesn't suffer from dust extinction and contamination, and therefore it can be used to explore our galaxy and its surroundings. We can use the density of the LISA detection to recover the scale parameters describing the shape of our galaxy, and we can use LISA sources to recover also to see the dwarf satellites surrounding us, but also, in principle, discover the new ones if there are any. And that's it.
Questions for Valeriya?
You mentioned that this survey wouldn't have contamination, but I was wondering if LISA would also pick up combinations with other compact objects like white dwarfs, neutron stars, or black holes, or any of the possible combinations.
Yes, yeah. So I was not extremely clear on the contamination point because I meant it in a way that any gravitational wave source can be used in the same way. I just used double white dwarfs because they are the most numerous. And for example, there are a couple of recent works on binary neutron stars, and the predictions are for Magellanic Clouds are like of a few or something. So double white dwarfs will be just overwhelm those rates.
What's the time scale of the single detection? What time does it take to get your signal to noise ratio?
Yeah, so these binaries are actually persistent sources. They will be, their signal will stay in the LISA band for the whole mission. So those with the highest frequency will start appearing in the LISA data after weeks. If I remember correctly, for example, Warren's 12-minute binary will appear, something like after 1 week already in LISA. And the rest will come as we accumulate cycles, so signal to noise.
Did it go 4 years to get down to 7?
For some of them. For some of them, yes, but those will be the lowest frequency, so larger orbital periods.
This is great talk. Many questions. So what if they extend the LISA lifetime to double it or 10 times? Would you gain a lot extra because you extend to the lower frequencies and then more white dwarfs there?
Yeah, so the major gain will be more detections at the low frequencies, and this is because of the previous question. Those need to overcome the background, and also LISA sensitivity, LISA noise curve is steeper at lower frequencies, so they need we need to observe them for more time so that they can come to detection threshold. And those will be binaries at larger orbital separations. And they can be, so for example, they can be black hole and neutron star binaries, or even helium stars and with white dwarf and neutron star components that just don't go as far in frequency. So we will potentially discover new gravitational or different gravitational wave sources. And that would be great because some of them are actually progenitors of the double white dwarfs that will appear earlier. So we would have progenitor and the system in the same data set.
I'm not a gravitational wave person, so I'm just wondering, do you get the distances to these sources directly from your
In gravitational waves, typically, so to get the distance, your source needs to evolve in frequency. So, for example, LIGO chirps gives you the measurement of the mass of the system, and from the mass, you can, by knowing the mass, orbital or gravitational wave frequency, you can recover the distance directly from the data.
Yeah, quick one. So, what is the typical astrometric accuracy that you can get with this time, and is that what's the factor mostly limiting it? Is it distance to these objects, or what is it?
Yeah. So you mean sky position?
Yeah.
So yeah, these are the typical values, and the main parameters that influence this are the signal to noise and the frequency. So higher frequencies would give you better sky position, and higher signal to noise as well. So again, I'm looking at the highest frequencies binaries, and those those would have distances and sky positions.
I think we need to move on to the next speaker, but she is around, so if you want to come talk to us. All right. And our second speaker today is Jingzhe. She's a postdoc who recently started here in the high energy division. Jing got her bachelor's degree from Northeastern University in China. She got her PhD in astronomy from the University of Florida, where she was working on the formation and evolution of high redshift dusty galaxies. She then went on to do a postdoc at UC Irvine, where she was working on Herschel dusty star-forming galaxies. And she really specializes in multi-wavelength studies of galaxies and their coevolution with supermassive black holes. So today she's going to be telling us about some of her work on dusty galaxies and obscured AGN.
Okay, good. Thank you very much. Today I'm going to talk about my research in the past few years, mostly on dusty galaxies. I will also talk about my current research on nearby Compton-thick AGN working with Pepe and Martin. First of all, why do we care about dust-obscured systems? We all know that dust absorbs UV optical light in a wavelength-dependent way. This plot shows the dust extinction curves in our Milky Way, LMC, SMC. The most prominent feature in our Milky Way extinction curve is this broad absorption bump centered around rest frame 2175 angstrom. The bump strength decreases from the Milky Way to the LMC to SMC, suggesting that there must be certain criteria for the bump carriers to exist. What are the ideal conditions and what kind of galaxies do they live in? I'll come back to this. Moving from the left to the right, the absorbed light hits the dust and dust re-radiates in the far infrared. That's a dust emission. Historically, the galaxies that were selected at bright sub-millimeter wavelength are known as sub-millimeter galaxies, or SMGs. SMGs are essentially dusty star-forming galaxies characterized by intense dust-enshrouded star formation, and they make up the bulk of the cosmic infrared background. This is a model plot, the cosmic star formation rate density as a function of redshift. Well, we all know by now that at least from a redshift 0 to 3, UV optical is insufficient to probe the total star formation, as a large fraction of star formation is obscured by dust, so we need infrared observations. But beyond redshift above 3, this part is basically unconstrained. So how important is obscured star formation at high redshift? Is the physics of star formation changing? On the right, this also shows the black hole accretion rate density. The star formation rate density and the black hole accretion rate density appear to trace each other in this range, but beyond redshift of 3, this is the current constraint on the black hole accretion rate. The evolution is much steeper than the star formation rate density. But current X-ray surveys are missing obscured AGN, and infrared observations are also highly incomplete. So we can't really tell the story here. So how do they evolve at the high redshift? Unfortunately, we probably have to wait until the next generation infrared and X-ray facilities to give a definite answer. But at least for now, what we can do is to identify and characterize dusty populations at high redshift from current large area surveys. So in the first part of my talk, I'm going to talk about dusty galaxies in emission. Then I'll talk about dusty populations selected by their dust absorption using the quasar absorption line technique, and also talk about nearby Compton-thick AGN. All right. During my PhD, I mostly work on gravitationally lensed DSFGs discovered by the South Pole Telescope. The background SMG is magnified and distorted by the foreground lensing galaxy, and you can see the red ALMA contours show the lensing arcs and multiple images, and the grayscale images show the foreground lensing galaxy. We have obtained multi-wavelength data, and I led the effort in characterizing their stellar properties. I developed a deblending technique to extract the background emission that's sometimes mixed with the foreground lensing galaxy. So in this case, after subtracting the foreground galaxy, a full Einstein ring is recovered in both IRAC bands coincident with the ALMA contours. Then I use a multi-wavelength SED fitting technique, including all the components, to derive their physical properties, such as their stellar masses and star formation rates. I just want to show you one key plot from this study. This is the specific star formation rate as a function of redshift. Compared to the star-forming main sequence, the SPT SMGs, the red ones, are all above the main sequence, suggesting that we're likely witnessing the ongoing strong starburst events that are most likely driven by major mergers. One of the SPT sources, 0346, even showed up in the Big Bang theory on the whiteboard. SPT 0346, the 3 black dots correspond to the 3 lensed images. You can check it out. It's in one of the episodes in season 3, I think. Why is this so special? This source is at redshift 5.7. It has a huge intrinsic higher luminosity, and the inferred star formation rate is about 4,000 solar masses per year, with a relatively small size. It turns out to be the highest infrared luminosity surface density or star formation rate surface density of any known galaxy at high redshift. This is just to show you the star formation rate versus size measurement compared to high redshift starbursts and quasar hosts. The dashed lines represent the constant star formation rate surface densities, and 0346 stands out here. This is a diagnostic plot, C+ to far area luminosity ratio versus dust temperature. Basically, star-forming galaxies occupy this region and AGN are down here. But 0346 has a dust temperature that's higher than that of typical SMGs, reaching into the AGN territory. So we suspected maybe there's AGN that's contributing to the huge IR luminosity that we see. So the question was, is it star formation dominated or AGN dominated? To look for an AGN, we asked for Chandra X-ray data. So this is the Chandra ACES full band image. A little bit surprising, we got non-detection, so we could only put an upper limit on the X-ray luminosity. This is another diagnostic plot, the far area luminosity versus X-ray luminosity. The typical dividing line between star formation dominated and AGN dominated systems is this line here, and 3 sigma upper limit of 0346 is here, pointing this way. You could say that it's consistent with being star formation dominated in the X-ray. However, we cannot completely rule out the existence of an AGN in the system. So we further obtained ATCA radial continuum data, another way to look for an AGN. But again, non-detections, only upper limits here. I also further performed the SED fitting, including AGN templates, to derive the fractional AGN contribution to the total IR luminosity. But again, a pure starburst SED remains the best fit. So that means the measured star formation rates reflect the true star formation rate. So we confirmed the starbursting nature of this galaxy, and a later follow-up data shows evidence that it's likely driven by a merger. Okay, that was SPT. In the past 2 years, I worked on Herschel-selected DSFGs. The largest Herschel extragalactic surveys, Atlas and Hermes, have selected a large number of DSFGs, mostly in the redshift range between 1 and 2. Selecting those with ultra-red colors, the so-called 500 micron risers, is very efficient in identifying a tail extending beyond redshift about 4. And we performed a Spitzer follow-up program of 300 Herschel ultra-red sources to constrain their stellar masses. This is the redshift distribution for our ultra-red sample based on photometric redshifts. The median redshift is about 3.7, and the well-studied A-list SMGs pick at the lower redshift, about 2. SPD SMGs also have a higher median redshift, but they are almost all gravitationally lensed, while the Herschel ultra-red sample is largely unlensed. On the right, this is just normalized by their sample sizes, again based on photometric redshifts. So I proposed an ALMA redshift survey to confirm the redshift distribution, especially the high redshift tail here. This is still ongoing. Before this survey, my collaborators had already obtained species for 12 individual sources. Here's an example of a gravitationally lensed ultra-red source at redshift 6.0. The background image is Spitzer IRAC, but what mostly you see here is from the foreground lensing galaxy. And the ALMA image shows the lensing arcs of the background SMG. On the right, this is an example of unlensed merging galaxies where the 2 major merger components are detected in IRAC. So we have obtained multi-wavelength data, including high-resolution interferometry data. And I focus my analysis on the unlensed sample because we can directly perform SED fitting to derive their physical properties. This is the stellar mass star formation relation for our ultra-red sample, and the gray points are the A-list SMGs at a lower redshift. So on average, our ultra-red sources have higher star formation rates and higher stellar masses, about a factor of 4 or 5. And compared to the Spiegel 2014 main sequence, they appear to lie on the main sequence, definitely on the high mass end, but that also depends on how you define the main sequence. We also identified the hyperluminous infrared galaxies that we'll do follow-up observations later. So we estimate their contribution to the cosmic star formation rate density and stellar mass density about 1%. It's not a significant fraction, but essentially this places a lower limit. So our sample contains the rare, intrinsically most dusty, luminous, massive galaxies that will certainly help us understand the physical drivers of extreme star formation in the early universe. Okay, so I've been talking about dusty galaxies in emission. Now let's move on to dusty galaxies in absorption. I'll introduce a relatively new population of quasar absorption line systems, quasar 2175 angstrom dust absorbers, or 2DAs. Just like other quasar absorption line systems, when a quasar slide happens to pass through an intervening galaxy, depending upon the impact parameter, the quasar may trace the IGM, CGM, or even the ISM of the intervening galaxy. If there happens to exist certain dust grains that are responsible for the 2175 angstrom bump, the intrinsic quasar spectrum will be modified by a dust extinction curve like this, and we may be able to see the absorption bump in the observed spectrum. So we initiated a project to search for the bump in the SESS surveys. And so far, we found about 700 bump candidates up to data release 12. And we conducted follow-up observations on 30 of them with KEK, MMT, and VLT spectrographs to further look at their chemical abundances, dust depletion patterns, as well as physical conditions. This is an example of a very strong Milky Way type bump. Here's a bump, and here's a strong magnesium 2 doublet. J1211, this one's at redshift 2.1. And here's a derived extinction curve. So in the KEK ESI spectrum, we detected a lot of metal absorption lines, mostly low ionization lines like silicon 2, iron 2, or zinc 2. For this one, we also obtained high-resolution VLT UV spectrum where we detected multiple velocity components. This spectrum also covers the H1 lemma alpha absorption, and the H1 column density of 21 qualifies it as a damped lemma alpha system. So with the H1 column density, we are able to derive the absolute metal abundances. So this shows the metallicity in terms of zinc abundance versus H1 column density. J1211 has a metallicity that's comparable to that of the Milky Way ISM, but higher than DLA's. This is the depletion pattern of different elements. This pattern resembles that of the Milky Way disk clouds, somewhere between the warm disk and the cool disk. The iron to zinc ratio is a commonly used depletion level indicator. The lower the value, the more heavily metals are depleted onto dust grains. This very high depletion level supports the existence of dust grains, and therefore the observed strong 2DA. It's remarkable that we simultaneously detected multiple C1 fine structure lines in the same system. Actually, C1 is detected in all the 2DAs. As long as it's covered in the spectrum, it's always detected. C1 fine structure lines can be used to probe the physical conditions in the absorbing galaxies, like their volume densities and temperatures. C1 is also an excellent tracer of molecular gas. Actually, we have a tentative detection of CO absorption lines. It's promising that we'll be able to detect their corresponding emission lines with ALMA, for example. I further performed a correlation analysis between metallicity, depletion, and velocity width for the sample. This is again metallicity versus H1 column density, and the 2DAs are among the highest metallicities at all H1 column densities. Some are DLAs and some are sub-DLAs, but they all have relatively high H1 content. This is metallicity versus iron to zinc ratio. Again, depletion level indicator, and there's an anti-correlation here. The 2DAs occupy the region with both high metallicity and high depletion. The last one is metallicity versus velocity width. A clear correlation here. This correlation is often interpreted as a well-established mass metallicity relation. And again, the 2DAs occupy at the high end. So suggesting that they're expected to be more massive than DLA or sub-DLA galaxies. But this is all based on absorption analysis. To really establish this population and compare with emission-selected galaxies, we need to detect their emission counterparts. So I proposed HSD direct imaging and grism spectroscopy to look for the host galaxy of the strong 2D I just showed you. This is a quasar image. If we take a closer look, a companion very close to the quasar sightline is reviewed, only 0.65 arcseconds, and its spectrum is also detected. So I extracted the spectrum and performed template fitting to determine the redshift. This redshift is in excellent agreement with the absorption redshift. So we have confirmed the host galaxy of a 2DA at high redshift for the first time. And we can learn a lot of things from this. From the image, we know that the impact parameter is only about 5.5 kiloparsecs. This is already probing the ISM of the galaxy. And this spectrum is dominated by a continuum with weak emission lines and Balmer absorption lines. And the O3-based star formation rate is about 9 solar masses per year, and the stellar mass is about 5 times 10 to the 10 solar masses. So this host galaxy is confirmed to be a chemically enriched, evolved, massive galaxy that's likely in the transition from a blue star-forming galaxy to a red quiescent galaxy, the so-called post-starburst. I further compared its star formation rate with emission-selected galaxies at similar redshifts. J1211 lies somewhere between Lama-alpha emitters and Lama-break galaxies, but this is based on the unobscured star formation rate. We don't know the level of obscured star formation yet. Actually, people haven't looked at the dust emission of absorption-selected galaxies. So to probe the far-infrared dust emission and constrain the obscured star formation of absorption-selected galaxies, I performed Herschel image stacking of magnesium-2 quasar absorbers. Dust has long been known to exist in magnesium-2 absorbers, and there are a much more abundant population than 2DAs. So here I did the stacking at the 5 Herschel bands. After subtracting the contribution from the central quasar, we do see residual signals at the long wavelength bands. So I extracted the excess photometry and performed far-infrared SED fitting to derive their far-infrared properties, most importantly, the total IR luminosity. The magnesium-2 absorbers at the 3 redshift beings, the red stars, they all have infrared luminosities in the range of luminous infrared galaxies, which are comparable to those of emission-selected galaxies like Lama-break galaxies or UV-selected galaxies. They are definitely less extreme than SMGs, which are supposed to be here, and higher than Lama-alpha emitters. So the dust-obscured star formation rates indicate that the obscured star formation is very important and must be taken into account to obtain the total star formation rates. Actually, people have found that magnesium-2 absorbers appear to trace the cosmic star formation rate density, but this is based on the unobscured star formation rate. So it's likely that they also trace the obscured star formation rate density. So probing the far-infrared emission of absorption-selected galaxies provides a new way and reveals a hidden population that contributes to the cosmic obscured star formation. And future ALMA surveys of magnesium-2 absorbers will constrain the obscured star formation rate density at this wavelength range. All right, putting more constraints on the high redshift frontier is very important, but now I feel like it's more urgent to better understand the AGN host galaxy connection in nearby AGN, where detailed physical processes can be learned. So I'm currently working on 7 nearby Compton-thick AGN with joint Chandra and new star observations. The recent discovery of extended kiloparsec scale hard X-ray emission challenges the standard AGN unified model. So studying this, we'll be able to provide physical constraints on the obscuring torus, and also this gives clues to how the supermassive black hole impacts the host galaxy on larger scales. Mackenzie already gave an excellent talk on this topic a couple weeks ago. I won't be going to the details of the techniques. I just want to draw your attention to one source, ESO 137 G034. It's a S0 to S8 galaxy hosting a SSFR-z nucleus. This is the HST optical band image where you see a prominent dust line across the entire galaxy. This is the oxygen-3 emission line map where you see a Z or S-shaped morphology with the ionization cones or bicone structure in the inner region, and also you have the tails extending out to the north and south. And our Chandra data also show extended emission, and this also aligns with the inner part of the oxygen 3 map. This is a 3 to 7 kV hardband only. We still see excess counts in the extended region, but this is less significant than the soft X-ray. This one, we have multi-wavelength data that we can do study their multi-phase ISM, the morphology, excitation mechanisms, kinematics to understand the feeding and the feeding feedback mechanisms. So this is work in progress. Hopefully, I'll come back to report the final results, so please stay tuned. I will just leave the summary slide here, and thank you very much. Oh, very clear.
I might have missed that, but you said you have evidence that the stuff on dusty galaxies are driven by major mergers.
Mm-hmm.
What kind of evidence is this?
So we have ALMA CO data that, because this is a gravitationally lensed source, we have to do source plane reconstruction. After that, we see like 2 components. Yeah. Yeah. Maybe I have a question for you. So for the yes, so for the Herschel selected DSFGs, so I'm particularly interested to see whether they also contain obscured AGN. That's very possible because you have this huge IR luminosity. So I'm asking if a good idea to ask for a big chunk of Chandra data to look at that. Yeah, that's right. Good. Okay.
All right. If there's no more questions, then let's thank you again.
It's hard. I know that you asked a question in the audience too. Hi, Rachel. Didn't see you sitting there. Yeah, I just waiting for the second.
I already gave this talk to my group, so they didn't ask questions. They asked a lot of questions.
We'll put it here.
Okay. So people heard me talking?
Huh?
So people heard me talking after the talk?
It should have it.